Now that we have some basic rules for analyzing transistor circuits, let's look at a couple simple examples and apply what we've learned. So here are two different examples of NPN bipolar transistor circuits. And for both of these, we'll assume that our beta is approximately 100. Okay, so here's our first circuit. 3 volts on the base, 10 volts on the collector, and a 1K resistor to ground from the emitter. So the first thing we want to do is figure out what transistor mode we are in. And to do that, we want to look at what's going on with this base emitter diode, right? So if we imagine that there's a diode, so ignore the collector, imagine that there's a diode between 3 volts and our 1K resistor and ground. Is that diode going to be on or off? Well, from our diode stuff, if you actually apply the diode rules, you will see, or you can just kind of look at it and correctly guess, the diode is going to be on. So that means we are going to be either in active mode or saturation. So how do we figure out which one? Well, we can put that on pause for a second because we can apply this diode being on to figure out one piece of information. So if this diode is on, we have a 0.7 volt drop from the base to the emitter, which means that this voltage is going to be 3 minus 0.7, which equals 2.3 volts. So at this point, we have 2.3 volts. Now, what are we in active or saturated mode? Well, we know the collector voltage, we know the emitter voltage. There is a big difference between these two, right? VE minus VC, VC minus VE is equal to 10 minus 2.3, which is 7.7 volts. That is much bigger than 0.2, which is what it would be if we were saturated. So we are definitely in active mode. Okay, so now we're almost done with this. So we have 2.3 volts across this 1K resistor, which means we have a current in our emitter of 2.3 volts divided by 1,000. So that's 2.3 milliamps of current. And because we're in active mode and a beta of 100, we know that our base current is a factor of 100 below that. So that's 23 milliamps divided by 100, which is going to be, 2.3 milliamps divided by 100 gives us a current of 23 microamps in the base. Lastly, the collector current, well, that, we know this current plus this current plus this current has to equal this current. So if we only need things to be precise to roughly 1%, it is enough to just say our collector current is just equal to the emitter current. This is also equal to 2.3 milliamps. If we were trying to be really careful, it would really be 2.3 minus 23 microamps. So this would be like 2.28 milliamps or something like that. But, our little model of the diode conduction is already it's probably only good to 1% or so anyway. So, leaving this as 2.3 milliamps is precise enough for our purposes in 315. Anyway, so that's a complete analysis of this circuit on the left. All right, let's do this one on the right. So we're going to start by doing a similar sort of thing. We're going to look at our base emitter diode and see if it is on or off. So here we have 10 volts, a 10K resistor in the base, and then ground. So that diode is also on. And now we want to see if we are in active mode or saturation. Well, we don't need to know this to figure out a couple other things. So if our diode is on and this emitter voltage is 0 volts, then we know that our base voltage has to be 0.7 volts higher than that, right? Because we're going, across the diode in the upstream direction. So VB is 0.7 volts. So if that's true, we have 10 volts here and 0.7 volts here. So the current through this resistor, that is the base current, the base current is equal to V over R, so that's 10 minus 0.7 divided by 10 kiloohms. So that is 9.3 over 10 kiloohms, which is 0.93 milliamps of current in the base. So this is, I'll draw on the other side so we have a little more room, I guess. So this current is 0.93 milliamps into the base. All right, I'll erase that. So if we want to figure out if it's an active or saturated, we can, one other question, or one thing we can look at is what would it take for us to be in active mode? So let's say, is it in active mode? If so, then I at the collector is approximately equal to beta times the current into the base. And if that were true, that would be 100 times 0.93 milliamps, which would be 93 milliamps. So would it be possible to have 93 milliamps of current through that resistor? Yes, if we had 93 volts across it. So in other words, for this to be true, we would need a change in voltage of 93 volts across our 1K resistor. Well, that cannot be true because this is 0 volts down here and our collector cannot be at some voltage below the emitter. The lowest it can be is a couple tenths of a volt above that. So this cannot be true because we're not going to have 93 volt difference across there. So we are not in active mode. We must be saturated. So if we are saturated, then our relationship IE equals beta IB, this is not true anymore. Our current is just something less than beta IB, and we don't have an equation for how much right off the bat. But we do know another thing, and that is that our collector emitter voltage, VCE, is equal to 0.2 of a volt, is equal to 0.2 volts. So if this is 0 volts, then our collector voltage is equal to 0.2 volts. So then we know the voltage difference across that 1K resistor, right? So the collector current is equal to the current through this resistor, which is 10 volts minus 0.2 volts divided by our 1K resistor. So that's going to be 9.8 milliamps. So we have 9.8 milliamps in the base, 0.93 milliamps in the base, 9.8 milliamps in the collector. And so out of the emitter, going here into ground, we must have 9.8 plus 0.93, which is going to be 10.7 milliamps or something like that flowing to ground. Okay, so that's two simple circuits to analyze. As simple as they are, even these circuits have applications, and we'll be talking about what circuits like this do in the coming videos.